I apologize in advance. Today is going to be a little more straight traditional lecture with no Tinkercad or super interactive stuff, and then hopefully things will get a little more lively again starting on Friday. So today we're going to be talking about robot navigation, and for not just today but a handful of the remaining lectures in this class, we're really going to be doing a overview single lecture of something you can go take an entire course on, right? So you can go take autonomous mobile robots as an entire semester course, which is kind of a popular follow-up to this one that I think is still offered in the spring, so a lot of you wouldn't be able to take until next year, depending on how that works. So today we're just going to be talking about a really high level at some different kind of navigation strategies or algorithms that you may or may not choose to employ in your robot. Okay, nothing here is mandatory. The very first one is basically what most of you either have implemented or are going to be implementing for milestone 1, called open loop navigation, meaning as opposed to a closed loop where you have sensor feedback, you are just kind of going for it, turning your robot on for saying drive forward for a certain amount of time, turn for a certain amount of time, and clearly that is okay over very short distances, right? The problem is the longer you do that, the more error accumulates, right? So if you tell it to drive straight, but you are off by just a degree, not a big deal if you're driving for just a foot, but that's kind of like if I close my eyes and I have a rough sense of how far I can walk in one step, and if I think I've turned 90 degrees, and I'm going to try and like walk to the back corner of the room by just closing my eyes and walking, right? Try this. It's hard to, the lighting just changed, that makes me nervous. But so I think I've made it around that table. Don't tell me. I'm going to go slowly and try not to trip. I apologize in advance if I'm going to walk into somebody. I'm going to lose my nerve and give up when I go, oh, see there, I tripped. I didn't even make it to this corner, right, before I kicked somebody. So the longer you do that with no feedback or correction, the faster error accumulates, okay? So that's kind of strategy 1, or kind of the easiest thing you can do is open loop, no sensor feedback. Maybe the pro there is that it's super simple and easy to implement. Con, drift from accumulated error. So you could approach the competition again. You do have to use the sensors to accomplish milestone 3 because we want you to demonstrate that you've used them, right? But you could then, for the actual competition day, attempt to program something like this, right? You have your competition board, and you could say, I want my robot to drive forward for 2 seconds, turn left 90 degrees, drive whatever the times are, drive forward for another 2 seconds, turn 180 degrees, and drive back across to try and sweep all the cubes. Again, the idea being that only works perfectly if you get your timing and distances exactly right? If you have it on for a little too long and you overshoot the cubes, then you're going to wind up driving back and forth up there, not getting the cubes. Or if you collide with the other robot, then it just totally throws everything out of whack, right? If you collide with the other robot and get turned 90 degrees, then maybe you're going to wind up driving off the board, or who knows. Okay, so probably not a great strategy for the competition. The next thing to kind of, at bare minimum, just avoid driving off the edge. Okay, you probably don't want your robot to just lemming off the edge of the board if you want a chance to stay on the board and gather the cubes, is what is kind of unofficially called the Roomba algorithm. Which is kind of loosely stated as just drive until you hit something and then turn around. Okay, so I don't know if any of you grew up with a Roomba at home or have one in your apartment now or something, but kind of basic idea, at least I don't know if the newer generations of Roombas actually have cameras and do mapping or kind of more advanced navigation, but initially they just had a bump sensor on the front and they would literally just drive until they hit a wall or a piece of furniture, turn and keep going. So they would kind of bounce around your floor like a ping pong ball, right? So not even worried about the color. If you just kind of start on one edge, drive until you hit the border, turn for some fixed amount of time, drive until you hit another border, drive until you hit another border, and so on. At least that is going to prevent you from going off the board. Okay, ideally you have at least one, probably two of these QTI sensors, which can detect that black border, and that's going to tell you, okay, my robot needs to turn. Which one of the sensors detects the border probably tells you which way you need to turn, right? So in theory, so this is kind of zooming in on the edge of the board, and there's your black border. If this is your robot and it's got the two sensors, right? If both sensors see the line at the same time, then that means, okay, you probably kind of drove perpendicular straight into the line. Maybe I want to back up and then turn around or do a 180 in place. Versus if you hit the line at kind of more of an oblique angle, so only one of the sensors saw the line, then okay, maybe I want to do, so if the left sensor sees the line, I want to do a right turn. Now, what happened now? Feel the cane? And if your right sensor sees the line, maybe you want to do a left turn, okay? So again, that is not taking anything into account about the other robot, the color border. Remember that the cubes are kind of going to be concentrated towards the color border, but bare minimum, avoid driving off the edge. Questions so far? Okay. And I guess I should have said, everything we're going to be talking about today is kind of conceptual with these diagrams. I'm not talking about how to actually implement this in code. That is up to you, right? You could use, we've talked about how these QTI sensors are basically a digital input. So you can use either polling or interrupts to detect the states of these sensors and then decide a corresponding action. Okay, this is going to lead into, I believe, something I talked about kind of really briefly earlier in the semester, a computing concept called a finite state machine, that if we have any computer science students in the class and you've learned about this more extensively in another class, please forgive me in advance for botching it, but kind of the mechanical engineering explanation here of a finite state machine is that we do not have this. What you don't have in this competition is an overhead camera that's giving you the XY position and orientation of your robot on the board, right? So we don't have a continuous state to always know exactly where the robot is. If you think of your robot's behavior, your basic robot design with two wheels, in terms of what your robot is doing, it can really be in one of four states. It can be driving forward, turning left, turning right, or driving backward. Those are the only four things your robot can be doing at any given time. So just for the sake of this example, we're going to ignore the driving backward part. Say we have a robot that only drives forward, turns left, or turns right. We can represent that robot's behavior with kind of a flow chart that represents a finite state machine. So I'm going to represent each of my states with a little circle like this. So I'm going to say state A is driving forward, state B is turning right, and state C is turning left, and I'm going to have kind of a start or initialize state where I kind of start off once at the beginning of the program. So say I start, immediately start driving forward, and then depending on my sensor inputs, I can have transitions between these three states. And so if you remember what I kind of drew here, right? So say if my left sensor sees the line, then I'm going to transition to the turning right state. So I would have an arrow going from drive forward to turning right and label that I'm not going to write out sees line each time, but this is left sensor sees line. That causes it to transition to the turning right state. But eventually, here I'm going to turn right far enough that neither sensor sees the line anymore, and then I'm going to transition back to driving straight. Okay. So, again, I'm not writing out the phrase sees line after every single one of these, but no sensors see line. Same thing for transitioning to the turning left state. If my right sensor sees the line, I'm going to transition to turning left, and then when no sensors see the line, I'm going to transition back to drive forward. Now, this isn't mapping out every single possible sensor combination between every single state, right? So when you look at these diagrams, you might see, well, what happens if I'm already driving forward and no sensors see the line, then nothing changes. That just keeps me in that state, right? If I'm already turning right and my left sensor still sees the line, then I'm going to stay in the turning right state. If I'm already turning left and my right sensor still sees the line, then I'm going to stay in the turning left state. Okay, now again, I haven't mapped out every single possible combination here. Like maybe there's something weird where you hit a corner and your left sensor sees the line and your right sensor doesn't, and then you start turning. So I'm in the turning right state, and I turn, but then my right sensor sees the line. I haven't mapped that one out, right? And again, I also haven't put in the driving backwards state here. So I just wanted to introduce you to this concept. This, again, is not mapping out every single possible scenario for your robot. Maybe your robot has other behaviors, right? If you have some mechanism for lifting things or whatever, additional motors doing stuff, or your motor, say you have a up or down positions for your mechanism, whatever it is, right? Then you could have different states where your robot is driving forward with the mechanism up, driving forward with the mechanism down, whatever it is, okay? But the point is that this is a way to kind of think about a system that can only be in a finite number of discrete states. If you go look at the Wikipedia page for finite state machines, it uses the example of like a subway turnstile, so something that locks until you put a quarter in or scan a card, then it unlocks to let you through, right? So it can only be in two states, locked or unlocked, but it can accept an input or sensor reading of kind of whether you're scanning your card or not. So these diagrams can grow to be much more complicated, but the point is that there's a difference between this and this, which is kind of more what you're used to seeing in dynamics or system dynamics, where you have some continuous state variable. And again, this is a concept, this doesn't translate directly to Arduino code. Okay, you need to kind of map out this concept in terms of how you want your robot to behave or how you want to change from one state to another. Then you need to figure out how you're going to implement that, either with if statements or interrupts or whatever it is. Okay, questions so far on the, I'm assuming most of you have not seen finite state machines before. This isn't, okay. Questions on this so far? Okay. Another way to kind of organize that information, which is showing equivalent information to what's in the graph, just organized differently, is a state transition, so what's called a state transition table, where across the top of that table you have your state. The rows are going to be the inputs, and then the cells are going to be the next state. So I should have labeled this current state across the top of the table. So say if we have our current states A, B, and C, which I've labeled up here, drive forward, turn right, and turn left, and then our inputs, generally X, Y, Z, but in this case that's no sensors, see the line, right sensor, sees the line, and left sensor sees the line. Now I can kind of go through and fill out this table based on the diagram I drew, right? So if my current state is A, I'm driving forward, and no sensors see the line, then my next state is still just A, I'm still driving forward. So that's this little kind of closed loop here, right? But if my right sensor sees the line and driving forward, then I'm going to transition to the turning left state. So my next state here would be C, versus if I'm driving forward and my left sensor sees the line, input C, then I'm going to transition to the turning right state, which is B. Okay, so that's the example for this column. You can go through and fill out the rest based on that diagram, but again, I mentioned for the diagram, I wasn't mapping out every possible scenario, so this one doesn't tell me what happens if I'm already turning right and then my right sensor sees the line, right? I didn't really define that behavior here. And again, maybe you just assume I don't think that's physically possible, so I'm just never going to deal with that possibility. Maybe depending on the geometry of your robot and where you have the sensors mounted, there is a possibility that you could have that. So really basically here, for the way I did this diagram, I don't have any transitions for what happens if both sensors see the line, or again, what happens if I'm in a certain state and the sensor I'm not expecting sees the line. So you should think about the logic of your code, and if those situations you haven't accounted for come up, what happens? Okay, is it physically impossible and you are confident that there is no physical way it could occur during the competition and you don't need to have a case for it in your code? Or do you think, okay, there's a chance that actually might happen and I need to have something to account for it? So I think another way to think about this in kind of as an aside in code, say if you have code for your robot to do stuff, if x equals 1, else if, don't worry about it exactly what x is here. So just x is some state or some combination of sensor inputs. Say you only really have if x equals 1, 2, or 3. Well, what if x equals 4, right? You didn't account for the case that x equals 4. But if you have that else condition on the end of your code, that's kind of the catch-all for anything that doesn't meet any of those prior 3 conditions, right? So think about this. You have your scenarios where you kind of expect that the physical geometry of the robot and the layout of what's going on makes sense, and you're going to react to those accordingly. What conditions could result in kind of your catch-all, and what do you want your robot to do if it gets there? If you don't have this at all, then that's risky, because the robot's just not going to know what to do, right? And again, we are talking about this kind of at a high-level general sense, because this is going to be different, for every robot, and there's not necessarily a right or wrong way to approach it. Questions? Okay. Now, so far we've just been talking about the line sensor, right? We haven't talked about the color sensor or the ultrasonic sensor yet. So in addition to sensors that can detect the black border, you have a blue side and a yellow side. And you can also detect what side you start on. You can detect that border, and you know that the cubes are kind of close to the border. Right? The cubes are going to be scattered in that middle third of the board. So between the 2 line sensors and the color sensor, you could, rather than just trying to program an open loop, you can use sensor feedback to try and get your robot towards this middle region of the board, right? And I think we talked about before, not necessarily the only 2 ways, but maybe the 2 first things that come to mind to me for do that are just drive forward as forward as fast as possible, straightforward, right? You get to choose the orientation of your robot when you put it down. It must start centered in the back of the board, but you're allowed to aim it straight ahead or to the side. You don't have to orient yourself first. So you can drive forward until you hit that border, and then you got to decide what to do, right? Do you turn left? Do you turn right? Do you back up and do something else, right? So you could drive forward until you hit the border, turn, try and stay close to the border to gather cubes until you hit the black border, then turn around and go the other way. Right? That's one strategy where you kind of drive straight for the middle. Another approach could be kind of more of a sweep approach where you start aim to the side. Again, you can put your robot aim 90 degrees to the side at the beginning, follow the border around the outside, and then kind of try and go across the middle and get as many cubes as possible, right? Risk there being that maybe, so risk here being that maybe your opponent went straight for the middle and got there first. Risk here being that maybe you both decided to go straight for the middle and you both crashed, right? Or if you both try this, if they go to the other side first, then maybe it's going to be whoever's faster and gets more cubes before you crash in the middle. If you both go to the same side first, again, maybe it's faster and whoever gets to the middle first, maybe it's whoever's heavier and manages to push the other robot out of the way if they collide. I don't know. We're going to find out on competition day. Okay, I just want, again, based on historical evidence of kind of how this project has run over the years and how you have to do the milestones, I've seen a lot of students kind of rely on this sort of hard-coded behavior that does not account for the presence of the other robot. This all goes out the window if you crash into the other robot. Okay? You assume you are in the process of driving forward afoot, but you just stall because the other robot is heavier, right? So you have gone nowhere, or you crash and you get turned 90 degrees. Whatever it is, this strategy no longer holds. Okay? So that brings in the color sensor for border detection, right? Color, and when I say border there, I'm referring to the border in the middle of the board as opposed to around the edge of the board. And then finally, you also have the ultrasonic sensor, which I cannot spell when I'm talking at the same time. Ultrasonic sensor. I keep saying ultrasonic sensor singular. Technically, you could use as many of these as your budget allows, right? If you want to have radial sensing around your robot, or you can mount one on a servo and make kind of a radar scanner thing. So you can have, it's totally up to you. You could have one just pointing straight forward, you could have one each side, you could have scanning one. That, again, in theory should allow you to detect the other robot. We've talked about this a bit. It's not perfect. The other robot may be irregularly shaped. Maybe they decide to make a stealth robot with acoustic foam. Who knows? It's probably not going to be great at detecting the individual cubes. And it's not going to give you millimeter or centimeter level precision to exactly the, or maybe centimeter level depending on the shape of the other robot. It's going to vary a bit. But should at least be able to tell you, okay, there's something close in front of me. Is the other robot within 10 or 20 centimeters in front of me? Yes or no? All right, so now, you throw that in, you've got border detection, you've got color detection. Now you've got a decision to make, right? You say you're following that idea where you're going to drive to the middle as fast as possible at the beginning, and your ultrasonic sensor detects the other robot either directly in front of you if you're only measuring position. You can also calculate velocity from this, right? You can keep track of sequential measurements and say, okay, that distance is decreasing. Either we are driving towards the other robot or it is coming towards us. How do you react? Are you confident that your robot is heavy enough or has some kind of BattleBot wedge type design that is going to lift the other robot or push it out of the way? Are you going to back off and change direction? Do you just say, you know, damn the torpedoes, full steam ahead, we're just going to crash into it? Again, I don't know what's going to work best, but you have the option of thinking about that. And again, historically, since there is not a mandatory milestone that requires this, my experience is that most teams have not done it. Okay, they just kind of don't account for the other robot in the competition, which again, then results in a lot of plans just going out the window on competition day when robots crash into each other. So, not mandatory. There is no graded milestone that requires use or demonstration of the ultrasonic sensor, but I kind of strongly encourage you to think about it, right? Unless you are extremely, again, confident that your robot is heavy enough that it's going to be able to push other robots around and you don't care where the other robot is, you probably want to have an idea or a strategy to react to whether the other robot is in front of you. Okay, and again, if you want to make sure you're not going to get T-boned or broadsided or whatever, maybe you want these things pointed to the side too, okay? Something else that we actually haven't mentioned much but are available in lab is what we call whisker sensors, which is basically just a bump sensor that will detect if you've crashed into something. So it's literally just, we draw the circuit diagram for a switch like that. It is literally that. It is a long wire that you attach to a screw on one end, and then when the wire gets pushed, it attaches to a screw it bumps into a screw on the other end and closes the electrical contact. So that kind of has very short range. It's not a distance sensor, but it's simpler to use because it just acts like a switch or a button. But it will, in theory, detect if you've crashed into the other robot. Okay, so those are, and I had forgotten to mention those before, they should be available in lab kind of to go with the robot kits. Okay, so if you now make a list of all of those sensors, this is kind of another way to think about this algorithmically. You can make a table with each input or sensor. So say you have your left QTI sensor, right QTI sensor, and then what the output can be. So, right, so the left QTI sensor output can be either high, precedes the border, or low for no border. Same thing for the right QTI sensor. You have the color sensor, which can see blue or yellow. So for each of these three sensors, say forget the ultrasonic sensor for now, each one of those has two possible outputs, so that's already 2 cubed possibilities for all possible combinations of those sensor inputs, right? Some of those may or may not be physically possible depending on the layout of the board, but I think for these you could get all 8 possible combinations, right? You can be on a color with no border, you can be on a color with 1 border, you can be on a color with both sensors on the border, you can be on a color with the other sensor on the border, right? So there's 4 combinations on 1 color for what the 2 QTI sensors can see, and then that's double because that can all happen on the other color. Okay, so there's 8 total possible states between those sensors. If you throw the sonar in there, now in theory that could be a continuous variable, but say you're just going to threshold it, right? Say I want to know if the other robot is less than 10 centimeters in front of me or not. Then in theory you've got another 2 possible states there, right? And now you're up to 2 to the 4th possible states. But here maybe some of those get a little less physically likely, right? Like if you have both sensors detecting the border and you're looking off the board, then if you see the other robot, then that means it is driven off the board, and in theory you no longer have to worry about it, right? So maybe you don't have to worry about all 16 possible states there, but you might want to think about, okay, which of these scenarios would I want to react to the other robot being in front of me? There are other, again, you might buy more sensors, you could add other things to this list. Another one that isn't really a sensor but kind of counts as an input is time, right? You have a 1-minute match. I've already heard some teams talking about, oh, we want to do something right at the start of the match, or do something when there's 10 seconds left, or something like that. So think about how, if you have a fixed time you want to do something, or you want to do something either after a fixed elapsed time or after an elapsed time since an event has occurred, okay, then this number of states could expand, and basically you want to make sure your code is accounting for these, and it's not, okay, we really only wrote code to handle these 2 or 3 things, and our robot just doesn't know how to react to the other 8 possible input combinations it could be encountering. Okay? Questions? As usual, it is impossible to get you guys to talk, so I'm going to give up for now. Since there were no questions, we got through that a lot faster than I thought we would. I think what we will do for the rest of today is kind of make it an optional working session for your groups. If you want to kind of talk strategy or ask me questions about this, If you'd rather just say, screw it, I want to go eat an early lunch and enjoy our endless winter in the snow flurries, you can go do that instead, okay? So again, I'll be here for questions. We got through that faster than I thought we would. So if you are sitting with your group and you kind of want to talk or haven't thought about some of these scenarios yet, again, with no guarantees that any of these approaches are going to win, but based on experience, there are things I've seen students not necessarily think about before, so that's why I wanted to devote some time to it. Okay? So.